Static electricity doesn't do anything. I mean, it goes zap, but that's all it does. Seriously, what good is it to anybody? Every year I'm asked the same question. If it can't work any of my devices, if you can store it, but you can't really use it for anything except Frankenstein, putting the fiction in science fiction, why do we need to study static electricity? So I like to open with this video to answer the question, why do we need to study static electricity? Well, here's why. Here comes the motorist getting out of her car. She's pulling on her sweater. Maybe she's got fleas under there, I don't know. But there she is with the gas-guzzling SUV, ready to fill up the tank. It's probably going to take a little while because it's a pretty big gas tank. So she's going to fill up the pump. Thank you very much for the gas station security camera footage, enabling us to see this whole interaction from start to finish. That's right, get the cheapest gasoline there is, and fill her up. Golly, what is that on her jeans? Why does she keep scratching and pulling at her stuff? Is she like having a bad clothes, bad jeans day? Well, this is going to take forever, so let's go into the car, slide across the seat, get that styrofoam cup of coffee from all the way across on the other side. Yeah, there, that's some good hot Java in the morning. All right, slide over the seat, put the coffee back, pull on the sweater. What is wrong with that sweater? Oh my God! Ladies and gentlemen, this is why we need to learn about static electricity, so that the next motorist who does this is not you, no, banging it on the concrete doesn't help. Lady flees to the station for help, and footage ends when the station attendant comes running to help put out the gasoline fire. Electricity, ladies and gentlemen, how not to end up like that. Let's quickly review everything we've ever learned from chemistry. Quickly fill in the blanks in your notes. Electric charge comes in two flavors. Negatively charges have two, and be careful now, positively charged have objects have what? Fill everything in, pause, press play to check your work. Electric charge comes in two flavors, positive and negative. Negatively charged objects have too many electrons. Careful, positively charged objects have too few electrons. No object ever gains or loses protons except in nuclear reactions. Think about those isotopes you did in chemistry. Too many electrons, too few electrons. You want to make a different isotope, add more neutrons, bad idea, it's going to be radioactive. But your atomic number comes from the number of protons. If you have more protons, you're a different atom entirely. All of that we're doing with electricity comes from electrons. Now, how do they interact with each other? Again, fill in the blank, pause, press play to check your work. Opposites attract. If you see attraction, there must be opposite charges. If you see repulsion, there must be like charges. Use the materials you have around the house to generate static electricity. Experiment with different kinds of cloth, metal, and plastic. If you have any balloons around, not helium balloons. Helium is really expensive and we're running out of it, and it's necessary for a lot of important scientific and medical equipment. Regular balloons, blow them out, decorate the house, have a COVID-19 party. You'll find some pretty dramatic results. We have an official kit here with clear acrylic plastic, PVC, which is polyvinyl chloride, the kind of plastic used in plumber's pipes, glass. I don't think this is silk. I think this is some sort of rayon or poly blend. It's a very smooth cloth. I know what this is. This is felt. Not only is it rough, it's made of wool.
And this is a bag.
This is fur. We took a vote as to whether it was fake fur or real fur. I hope it's fake. Shani thinks it's real. See what happens when you rub the PVC against the fur. Do you hear anything? What do you hear? Do you feel anything? What do you feel? Do you hear something?
I hear like it's crackling.
You hear the crackle crackle of the electrons jumping. Now wave the wand over the fur, nice and close. What do you see? Do you see the fur standing up?
I see it moving, but I don't see some of it standing up.
Let's try with the felt.
That sounds like you're cleaning something.
It does. Can you hear the crackling?
A little bit.
All right. Now wave the wand right over Emma's hair. Does it make Emma's hair stand up?
No, that's because you have a ponytail.
Can you see the fuzz? Following back and forth in the direction of the wand,
yeah.
we have created static electricity. Now you create static electricity on your house and hypothesize what method of charging works. Take notes on what did work and what didn't work. Notice that we could polish the glass until we're blue in the face and we won't see any kind of effect, not with any of the other materials. And whenever we use that nice smooth cloth, especially on glass, you can polish until your wrist is just about ready to fall out, but you won't hear any of the clack rattling. There's something about the glass, and there's something about that nice smooth polyester that is definitely ruining whatever it is we're trying to do to create the static electricity. Pause, enjoy your playtime, press play when you're ready. What did you find? Did rubbing a balloon on your little brother's hair make it stand on end? Did you find that anything that was incredibly smooth failed to cooperate? We're working on charging by friction. Many of you will felt the objects getting warm as you rub them together. Friction allows two neutral objects, as they scrape past each other, to knock electrons from one onto the other. Think about those models of the atom that you saw in chemistry class last year. We did the trans and the cis and all those little styrofoam balls on sticks sticking out all sorts of weird angles. Well, rub two styrofoam balls on sticks models past each other, and some of the styrofoam balls on sticks are going to get entangled and break off, and that's exactly what's happening to the molecules in materials that are charging by friction. Check it out. They're scraped off so that one side ends up more positive with fewer electrons, and one side ends up more negative with more electrons. You can call this the Triboelectric Effect if you want to sound really fancy and see if you can get some extra grant money, but it's really just charging by friction. And as you saw, materials with more friction will charge more efficiently. Glass is actually very, very good at gathering and retaining electric charge, but it has so little friction you'd have to be charging it for hours before you see what a good accumulator of charge it is. Were you able to figure out whether you had positive or negative charge? Us neither. We could see that they were opposite charges because the fur and the hair and the cloth were attracted to the wand. Charging by friction takes two neutral objects, scrapes electrons off of one and onto the other to make one positive and one negative. Who gains electrons and who loses them? Well, if it weren't for this series of data of many, many experiments that other people did in lab, we'd have no idea. This is the Triboelectric Series. Do not memorize it. Nobody ever memorizes it. You can look it up in your notes and on the web anytime you need it. It turns out that proteins tend to lose electrons by and large. You can picture proteins from biology class, those horrible zingy shapes with bits sticking out. Yeah, scrape two of those past each other, I can bet the electrons fall off. Glass tends to lose electrons. There's something about that silicon dioxide doped up with argon every 8 atoms or so that really tends to lose electrons. Nylon is a very complicated polymer. It tends to lose electrons. Notice the different proteins with us and the bunnies and the sheep and the silkworms and even the trees. If you take a wool hat and pull it onto your head and then pull it off again, who loses electrons? Who gains electrons? Consider it. Write down your hypothesis. Press play to check your work. Ready? Trick question. They both lose electrons. They both gain electrons. Anything that the hair loses falls onto the wool and is gained by the wool, and any electrons that the wool loses falls onto the hair and is gained by the hair. However, on the whole, human hair tends to lose more electrons than wool, so the hair losing electrons ends up more positive and the wool ends up more negative. Now, different question. You very, very foolishly put your wool hat in the dryer with a lot of cotton socks. I don't think the wool hat should go in the dryer, and if it does, it should be dried on a different setting. But if you did, and the wool and the cotton are rubbing against each other, who has what charge? Again, write down your hypothesis. Press play to check your work. Ready? Who loses electrons and who gains? Were you ready for me that time? They both lose and they both gain. However, wool loses more electrons, so it ends up more positive, whereas the cotton will end up more negative. Hey, wait a minute, didn't we say that wool was negative in the last example? We did. But since everything is losing and gaining electrons in the process, there's no reason that the same object gets the same charge every time. It's charged relative to the other surface. A much harder question is why it is in the winter that you throw back the sheets, cotton sheets rub on cotton sheets, and you see huge displays of static charge, blue lightning in the night that freak out your baby brother who doesn't know who it is. How is it that the cotton can make charge, two identical materials rubbing against each other? Again, write down your hypothesis. Press play to check your work. They both lose, they both gain. Cotton is an insulator. That's going to be the next set of notes you take. So different parts of the same cotton sheet can have different charges. On the whole, on the average, both sheets will have a neutral charge, but you can clearly see the electrons jumping, those are the sparks that you see, from the negative parts of one sheet to the positive parts of another. These materials tend not to lose electrons. They tend to keep their electrons very close and not have them knock off. Therefore, if they're not the one losing more, they must be the one gaining. Lucite plastic gains electrons, but not as much as those balloons you had around the house, not as much as hard rubber, not as much as synthetic fabrics. Notice here we had a common thread of protein. Here we have a common thread of poly, very complicated synthetic molecules, polyester, polystyrene, polyurethane, that's the kind of shiny plastic that's used to make trashy raincoats, polyethylene, polyvinyl chloride. The material that tends to gain electrons the most it's the kind of black plastic you see in magician's wands. Ebonite is the best gainer and worst loser of electrons there is, which is why magicians can polish up that magic wand just like we did in the demo and use it to do magic tricks. Go to the balloons and static electricity activity on PhET Interactive Simulations, phet.colorado.edu, and see what you can do with charging by friction. Rub, 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 and see how opposites attract and how the charges distribute themselves. So, what happened to our poor motorist? What did she do that caused that scary gasoline fire? It's not that uncommon of a problem. Remember the way she kept tugging on her sweater when she got out of the car? She was covered with static already. It was in her clothes, it was probably in her hair, and when she got back into her car after pumping gas, she went and slid across the seat. Look at that static on her jeans. She grabbed her styrofoam cup of coffee, which we know styrofoam charges very well by friction. It's not smooth and it gains electrons beautifully. She slid back across a second time, covering herself with even more static than she had already. There's the static, there's the static, there's the spark, and there's the fire, which is why nowadays all the signs not only say don't use your cell phone in a gas station unless you particularly want to blow up today, they will tell you to discharge your static before fueling. Before using the pump, touch any metal on the car away from the fuel filter. If you please, touch it with a bare hand. Once you know something about conductors and insulators, you'll recognize this as grounding, getting rid of the excess charge by giving it to the ground, which is so big it doesn't care. Do not re-enter your vehicle while gasoline is pumping. There's nothing wrong with the inside of your vehicle, but unless you can float or you can fly, you're going to be charging yourself by friction as you scooch across the street. Thus, this can recharge your body with static electricity. If you must re-enter your vehicle, discharge static electricity again before touching the pump nozzle.